But anyway, we need to figure out how to assume the cross section of concrete. We have cross section, we have width B, and we have total or overall depth, which called T, or sometimes H, the whole or the overall depth. By the way, the cross-section width, go ahead and assume as you like. The common values 10, 12, or 14 inch. So probably it can be 16, but I think the minimum is 10. And your number should be even number. We cannot assume 11. Just for construction, 13, 15, probably 15, yes. But most of the time, this number is even number. The common width, 10, 12, or 14 inch. This is for B. For H, based on the beam. If you are talking about simply supported beam, you have a beam simply supported between this support, and this beam has span L. Go ahead and divide L by 16. You can figure out the overall depth. If you are talking about span like this one, so for this span, what do you think? It's continuous from this side. So if we are talking about one end continuous, so span this L divide 18.5. I'm not talking about my numbers. I'm talking about ACI recommendation. ACI 318 recommendation to select or assume H overall depth. Please don't assume any H below these numbers. You can go over. If this table give you a number 25, for example, you can assume 830. That's fine. You can assume 827. That's fine. But don't assume a number below these limits. If your beam like this, I'm talking about this span, I'm sorry. This span, if you are looking for this span has continuous from two ends. From this side, it's continuous. We have another span here. At this side, we have another span here. So both ends continuous. So this span L divide 21, I can figure out the overall depth. If you are talking about cantilever, do you remember cantilever? Anybody remember? Cantilever means we have a beam fixed from one side and free from the other side. So the span of this cantilever divide 8. So let me do an example. Just example. We have a continuous beam. We have spans. This one is 10 feet. This one is 12 feet. This one is 10 feet. This one is 14 feet. I'm sorry, let me change these numbers a little bit. This one is 12 feet, and this one is 10 feet. Go ahead and assume cross section. So we need to satisfy the ACI limits. I'm gonna assume B equal 14 inch. We have three values, 10, 12, 14. I'm gonna assume it 14. So I'm looking for overall depth. If you start with this span, what is the assumed number? What do you think? This span is simply supported? I don't think so, because this span is continuous from this side. We have another span continuous. So you are, in this case, one end continuous. So your overall depth can be L divide 18.5. So this one, I'm going to assume H equal span divide 18.5. This one in feet, I'm going to multiply it by 12 to be in inch and divide this number by 18.5. So 120 divide 18.5. So the limit here will be 6.5 inch. Very small. That's fine. What about this span? What do you think about this span? I think this span is continuous from this side and this side, from this end and this end. So you are talking about this case. Both ends continuous. So span divide 21. So H equal span, which is 12, divide 21. But this 12 in feet, I'm gonna multiply it by 12 to be in inch. So 144 divide 21, your value will be 6.85. The same here, the same here. So I'm done. So please, I'm gonna assume cross section with width 14. What about the overall depth? I have a limit 6.5 and 6.85, so the limit will be 6.85. I'm gonna assume it 20 inch. I'm gonna assume it 24 inch. I'm gonna assume it 30 inch. That's fine. But please don't go below this number. So we have a guide. We have a guide. We don't need to go below this limit, but you can go over. How much over? It's up to you. So I'm good. If anybody assume 24, 20, 30, 25, 26, 22, 18, 16, that's fine. All of these numbers are good. Any question for this point? Any question for this point? Oliver, do you have any question? One more example. Yes, yes. I'm talking about the minimum. You cannot go below this number. Let's talk one more example. We have a cantilever with span 30 feet. How can I assume the cross section for this beam? If you follow the limits for ACI, everything will be good. We are on the safe side. So I'm gonna assume this width 12. Okay, that's fine. What about the overall depth? Do you have a limit? We should. So your limit for a cantilever, because this beam is a cantilever, it's only fixed from one side and free from the other side. So you are in a cantilever case. So span divide 8. So H, the overall depth, equal span 30 feet. I'm gonna multiply it by 12 to be an inch, divide 8. So your overall depth should be no less than 45 inch. No less than this number. So I'm gonna assume it 45. Too much. And the 30 feet also is too much. Okay, so 45, 46, 50, it's up to you. This one, 12, 14, it's up to you. Sometimes 16, it's okay, no problem. So these limits just to guide you to assume the correct overall depth. Okay. Your question, Burak. This is overall depth. We have steel reinforcement. We have steel reinforcement at this location with distance called depth, D. What we did, overall depth, which is H, or sometimes T, over all depth. How can I get the depth? So we need to subtract this little distance. Do you remember what is the name of this little distance? Do you remember? Cover. Yes, thank you, Cody. This called cover. So we have some guide also to help you to figure out what is the perfect value of cover. According also to ACI-318. But before, do you remember what is the main purpose of the concrete cover? Why? Why we didn't put steel reinforcement like this? Why? At the bottom, exactly, of the cross section. So anybody can watch it. And we can watch it for any reason. So why we didn't do this? Why we put reinforcement embedded in concrete with a cover? For corrosion, to prevent corrosion. Yeah, the corrosion is a very bad attack issue for any building. So concrete cover protect reinforcement from corrosion. Insulation the steel from extreme heat if you have fire. I think the effect of fire on steel is bigger than the effect of fire on concrete. So we need to protect steel reinforcement from any extreme condition, like corrosion, like fire, all of these, like salt attack, for freezing, all of this stuff. So I think if you have a concrete rested directly on ground, on soil, will be different about concrete on a building on second floor or third floor. It will be completely different from a bridge in contact with water. So we have different values of cover. But right now we are talking about beams not exposed to weather or in contact with ground. Beam inside the floor, inside your apartment, inside your building. We have we don't have exposure, direct exposure to weather. So beams will have minimum cover equal 1.5 inch. Minimum. I said minimum. That means you can go over this number, but you cannot go below this number. And one more thing. This cover from the bottom of the steel reinforcement to the bottom of the cross section. This is the cover provided in this table. But we are looking for this distance from the center line of the steel reinforcement to the bottom. So we have to add half diameter of the steel bars. So for my opinion, I don't care about half diameter or all of this stuff. If this cover minimum is 1.5, I'm gonna assume this cover 2 inch or 2.5 inch. I'm gonna increase it by 0.5 inch or 1 inch more. For example, one day we will talk about foundation. We have foundation which is cast against and has a direct contact with ground. So at this moment, your cover must be 3 inch. So I'm gonna increase it a little bit, 0.5, 1 inch more. So I'm gonna assume it 4 inch. So your question, Burak, how can I assume the concrete cover? Commonly for beams, the minimum is 1.5, but this minimum represents clear cover from the bottom surface of the steel reinforcement to the bottom surface of the cross section. But I'm looking for the distance between this center line to the bottom surface, so I'm gonna increase this number a little bit more, which is half diameter. It should be half diameter or more. So once you figure out the cover, I can figure out the depth that will be used in design. So I didn't give you specific numbers. I'm giving you guides. So assume any missing data, but respect these limits. Okay? For depth, for overall depth, I didn't give you a specific number, but I give you a guide. Don't go below this number. For cover, I give you a limit. Please don't go below this limit. Go over this limit. Until this moment, do you have any more questions? Yes. This cover, which is given in this table, this limits from the bottom of the steel. Here is the steel reinforcement. It's a circle cross section. So from the bottom to the bottom of the cross section. This is a clear distance. But to figure out the depth, this depth is measured from the center line of the reinforcement to the top of the cross section. So we need to add this cover by a little bit of this radius or half the diameter. Okay. Okay. What else? We covered last week 2 situations. The first situation, everything is given. You have a cross section with dimensions. Everything is given. Even area steel is given. And you can figure out what is the design bending moment. Do you remember? Design bending moment. If I'm talking about design, so I'm talking about MN time phase reduction factor. And your applied moment must be smaller than or equal the design moment. So this one is applied moment on the structure or on the beam. And this value can be done using structure analysis. This one called design moment. And this design moment depend on what is the cross-section dimension, what is the given area steel. So, and this moment, applied moment on the beam from structure analysis coming from the external load, the load on the building. So we have moment from external load, we have design moment coming from the dimension and cross section and the exterior reinforcement of the in the cross section. This is the first situation. The second situation, no, area steel is missed. And M ultimate is known. Can we figure out the required area steel? We need to design exactly what is the required area steel for this moment. Okay, go ahead and get this number. Use a table to figure out the value of rho, steel reinforcement ratio. And rho equal area steel divide B times D. You have rho, you have B and D. I can figure out the area steel. Nancy, I'm not sure you are here or not. You asked me a question about once I get area steel, how can I convert it to numbers of bar? You have to select your size of bar. You have number 3, you have number 4, you have number 5, you have number 6, you have number 7, you have number 8, you have number 10, you have number 11, you have number 12. Select any size. It's up to you. It's up to you. So no, I'm not talking only about number 3 or 4 or 5 only. No, you can go over for 6, 7, 8 and get your number. I prefer to select a size that give me a good number. Not too much, or not very, very small number. So very, very small number like 2. 2 is very, very low number. 10 bars is too much. So I'm gonna assume 6, 5, 4. All of these numbers is good. Okay. Okay. We have, just to remind you for something, we learned from structure analysis, and I can remember all of this stuff. If I have simply supported beam, I'm talking about solving with hand, without any software, without reason. If you have simply supported beam with uniform distributed W, the bending moment is parabola. And this value of moment equal WL square over 8. If you have simply supported beam with concentrated load P, at mid-span, your moment equal PL over 4. If this moment, your moment here will be looks like triangle, and this vertex of the triangle at the same location of the load. And this value of moment equal PL over 4. If this concentrated load not at mid-span, so we have distance A, distance B, and the total distance is L. So your bending moment will be triangle. Don't forget the vertex of the triangle at the same location of the applied force. This maximum moment will be PAB divide L. I highly recommend to keep these diagrams and these values in your mind all the time. If you have concentrated load, if you have distributed load, first of all, I'm talking about simply supported beam. So beam supported by 2 supports only. If you have distributed load, your moment looks like parabola. Your maximum moment here, WL square over 8. If you have concentrated load at mid-span, your moment will be triangle. The vertex of the triangle at the location of the concentrated load, which is at the mid-span, your moment will be PL divide 4. If you have concentrated load, but not at the mid-span, so we have distance A and distance B, and the total distance is L, your moment will be triangle also. The vertex of the triangle at the location of the concentrated load, your maximum moment will be PAB divide L. Two bars is too low number. Try 4, 5, 6. These numbers is good. Two bars is good, still good also. 2 bars is still good. I cannot say anything. But 1 bar is wrong. Don't try to use 1 bar. 1 bar will make some eccentricity. So the minimum number is 2. I can agree. It's okay. It's okay, but we don't prefer. Okay? Okay. But if you have a beam like this one, or like this one, do you remember something from last semester about structure analysis? These beams, if you have more than 2 supports, you are talking about something called indeterminate structure. We have many reactions, we have many things, so we cannot solve these structures with simple way. Okay, so if you have more than 1 span, 2 spans, 3 spans like this, ACI can help you to solve these beams using this table by providing simplified method of analysis. We don't need to go back to structure analysis and the methods used to solve indeterminate structure or using software. No, we don't have software, we don't have anything. So we need to figure out these values of moment in a very simple way. ACI can help you. Without going through this table, I'm gonna summarize all of this information. We have positive moment and we have negative moment. You remember positive moment at the top, negative moment at the bottom. So if you have 2 span, we have negative moment here. We have positive, negative, we have negative, and positive, and we have negative. I'm sorry. We have negative. This value based on this table will be W L square divide 24. This one will be W L square divide 14. This one will be the same, W L square divide 14. This one will be W L square divide 9. This one will be W L square divide 24. If you would like to draw it in a very simple way, if you have 2 span, we have here a little bit of negative moment. Then we have positive, negative, positive, and a little bit of negative. This one is WL squared divide 9, WL squared divide 24, WL squared divide 14, WL squared divide 14, WL squared divide 24. W is the applied force. L, span of this beam, square divide 4, divide 14. If your beam, it's not 2 span. No, we have many spans, 3 minimum, 4, 5, 6, 7, 8 span, whatever. The same shape of moment. We have positive here. We have negative here. We have another negative. We have negative. We have negative. We have positive. we have positive, and so on. This negative moment will be WL squared divide 24. This one will be the WL squared divide 10. This one will be WL squared divide 11. This one will be WL squared divide 11, WL squared divide 11, and so on. This one will be WL squared divide 14. This one will be WL squared divide 16, WL squared divide 16, and so on. So for continuous beam or more than two span, can you see? After the first one, this is the edge span or the first span. We have different values. WL squared divide 24, W squared divide 14, W squared divide 10. But after this, the same. Everything the same. W squared divide 11, W squared divide 16. W squared divide 11, W squared divide 16. This is a positive moment. This is a negative moment. This is the translation of all of these values in this table. Guys, remember, sometimes we need to figure out the value of moment to figure out the value of area steel. So sometimes the first step, we need to figure out what is the applied moment. We don't need to go back to structure analysis. We don't need to go back to RISA. So ACI give you few hints. Can give you the value of moment if you have two span beam or more than two span. If you are talking about positive moment, we have expression for moment. If you are talking about negative moment, we have expression for moment for two span. For three span, you need to figure out, are you talking about the first span or the next spans? If you are talking about the first span, are you talking about positive or negative moment? Any questions so far? Any question? Okay. I will go back to this one by example, but just a second. This slide, which is a slide number 6, is critical. Because if you didn't understand this slide correctly, you will do fatal mistake in your construction. This one is critical. Please, everybody, pay attention. Everybody, please pay attention. Okay, we have a beam. This beam is supported on different supports. This beam under the effect of applied load by any method, structure analysis, RISA, simplified method using ACI, I am done. I draw bending moment diagram. That's right? That's right. This beam in the real life looks like this. This is a column. We have another column, which called support. We have another column. We have another column. This is a real beam, and this beam has a center line at the mid thickness. In United States, what we learned in structural analysis and the common direction of moment is drawn on the compression side. Sometimes we have here positive moment, we have here negative moment, we have positive, we have negative, we have positive. I'm talking about moment and sign convention in United States. Moment is drawn on the compression side of the member. So at this part, your bending moment is drawn above or below the member. I'm talking about this part. I think this moment is drawn above. So compression side will be above or below the beam. So compression side will be above. Okay, let me talk about this one from here to here. Your bending moment is drawn like this. Based on this information, the moment is drawn on the compression side. So I think your compression will be here. From this part, your compression will be here. For this part, your compression will be down. For this part, your compression will be up. Anybody has any question for this point? It's very simple. Go ahead and draw your moment. Positive moment is at the top. Negative moment at the bottom. Once you draw your moment is drawn on the compression side. Once you find the moment, you will find the compression side. Guys, just to remind you, if you have cross section, we have moment. So we have neutral axis. So we have one side in tension and one side in compression. Sometimes your moment is coming like this. So your tension will be at the top and your tension sometimes will be at the bottom. Your compression at the bottom and your neutral axis is here. So we need to determine, are you in this case or are you in this case? Why? The answer is very simple. Because if you are in this case, your reinforcement must be here at the tension side. If you are in this case, your reinforcement must be here on the tension side. That's right. One more time. Guys, we used that your moment looks like this. At this tail, we have tension. At this head, we have compression. In between, we have neutral axis. So if you can decide which side in tension, which side in compression, I can figure out where can I put my steel reinforcement. Sometimes we have a different situation. Your moment looks, your beam and your moment looks like this. So at this tail, we have tension. At this head, we have compression. In between, we have neutral axis. So tension in this case at the top. So steel reinforcement must be at the top. So steel reinforcement is at the tension side. We have information here. Steel reinforcement is put at the tension side. So can anybody tell me where can I figure out where is the tension side? Okay, I cannot, but what I can do, I can let you know where is the compression side. If you can figure out where is the compression side, I can figure out where is the tension side. If the compression side at the top, tension will be at the bottom. If the compression side at the bottom, tension will be at the top. That's it. Bending moment diagram can help you to figure it out. Based on this information, bending moment diagram is drawn on the compression side. Just very simple. Just very simple. For this part, bending moment diagram is drawn at the top of the beam. That means at the top of the beam, we have compression. That means the tension will be at the bottom. So steel reinforcement must be here. For this part of the beam. Bending moment diagram is drawn below the beam. So compression side will be down. That means tension side will be at the top. So steel reinforcement will be here. For this part of the beam, we have bending moment diagram at the top of the beam, which is positive. So compression will be at the top. That means tension will be at the bottom. So steel reinforcement will be at the bottom. For this part of the beam, bending moment diagram is drawn at the bottom. So compression at the bottom. Once you find moment, you find compression side. So I can figure out where is the tension side. Will be at the top. So steel reinforcement will be at the top. For this part of the beam, bending moment diagram is at the top. So compression will be at the top. So tension will be at the bottom. So steel reinforcement is at the bottom. These information are critical. These information are important, significant to your understanding. Guys, did you get it? It looks like you are playing. Once you draw your bending moment diagram, the bending moment diagram can tell you where is the compression side. So I can figure out the tension side on the other side. Guys, did you get it? Okay. Okay. So you told me if you have a moment, I can figure out the value of rho. I can figure out the area steel. That's right? That's right. Okay, you are done. We have a moment here. Go ahead and get rho. Go ahead and get area steel for these bars only. We have a moment here. Go ahead and get rho. Go ahead and get area steel for steel reinforcement at this location only. We have a moment here. So I can figure out rho, area steel for these bars only. And keep going. So based on the moment diagram, I can figure out where can I put my steel reinforcement. Then based on the value of the bending moment, I can figure out how many bars I need for this part of the beam. Let me do this example. This example is very important. We have a beam. We need to design the shown reinforced concrete beam by determining. Nothing is given, except we have a beam with 3 spans and 4 supports. We need to look out what is the cross-section dimension, what is the required area steel, if yield 60,000, F prime C 4,000, and each span 20 feet. Each span here 20 feet, 20 feet, 20 feet. Given we have a dead load, live load, and we have a hint, this dead load, which is 1.5 kb per foot, not including the on weight of the beam. So first step, we need to assume the cross section. What is the value of B? It's up to you. 10, 12, 14. It's up to you. I'm gonna assume it 14. It's up to me. What is the value of overall depth? Okay, for this span only, this span is continuous from one side, this side only. So your overall depth will be one end continuous will be L divided 18.5. H equal this length divide 18.5. Don't forget this one in feet. I multiplied it by 12 to be in inch. This one will be 20 times 12 divide 18.5. This one will be 12.97. Please don't go below this number. For this span is continuous from this end and continuous from this end. So we are talking about both ends are continuous. So your H will be span divide 21, I think. Is it 21? Yes, 21. So this overall depth will be 20 times 12 divide 21 will be 11.42. So please go ahead and assume this overall depth and don't be below this number or even this number. So I'm gonna assume it. How much? 20? 20? It's up to you. 22, 17, I'm sorry, 16, 14. That's fine. So I'm gonna assume it 24. It's up to you. The common dimensions, you are talking about something in 20s. 20, 22, 24, 26, something in this range. We don't like to go below 20 because if, you know, more depth, less reinforcement. Less depth means more reinforcement. My question is for you. Do you think which one is more expensive? To buy steel reinforcement or to buy concrete? This question or the answer of this question will let you know why. The required is only 12.97, 11 point, and you assumed it 24. Why? I'm gonna try to assume too much reinforcement to make steel reinforcement little and little. Put this information in your mind. More depth, less reinforcement. Less depth means more reinforcement. Okay? If you don't care about how much it will cost, okay, go ahead and assume what you want. What else? Yeah, if you have steel reinforcement here, can you tell me what is the depth? Yeah, I can tell you. 24 minus 2 will be 22. Because for beams, where? For beams, I'm gonna assume the clear cover is 1.5. I'm gonna increase it a little bit to be 2 inch or 2.5 inch. It's up to you. Someone will assume this one 2.5. That's fine. So this one will be 21.5. That's fine. If you remember, I told you we don't have one specific solution for any problem. We don't have one specific solution because we are talking about design course. So everybody will have different scenario. So the first step, I assumed the cross section. Any question for this point? These calculations only for to guide you. That's it. Just to guide you. Any questions so far? Guys, this dead load does not include the on weight of the beam. So we need to figure out on weight of the beam. Anybody remember last time? I think last time. How can I calculate the on weight of a beam? On weight equal B divide 12 time T divide 12 time 1 inch, 1 feet length time gamma of concrete. Do you remember? So 14 inch divide 12, 24 inch divide 12, time 1. This is the volume. Time 150. 150 is the gamma of concrete, normal weight concrete. So the value of on weight, by the way, this value 150 pound per cubic feet, pound. So 14 divide 12 time 24 divide 12 time 1 time 150. This value equals 350 pound per foot. If you would like to convert it to kib per foot to be like this, divide it by 1000 will be 0.35 kib per foot. So your W ultimate equal 1.2 dead load plus 1.6 live load. We need to take factor of safety. Do you remember? Factor of safety. So we need to increase dead load by 20%, increase live load by 60%. So 1.2. What are the dead loads? We have given 1.5. We have on weight calculated 0.35. Nothing else. Plus 1.6 time live load 2.5. So your final answer will be plus 1.5 times 1.2 plus 1.6 to 2.5. This one will be 6.22 kib per foot. So guys, right now I have on this beam distributed uniform load W ultimate equal 6.22 kib per foot. So we learned how to figure out or assume the cross-section dimension, how to calculate the on weight, how to combine dead load plus live load and the take factor of safety. Then the final situation right now, we have a beam with uniform distributed load. How much? 6.22 kib per foot. Then what is the value of M ultimate? My question is, how many spans here? Is it 2 or 3? How many spans? 3 spans? You are in this situation. W 6.22. L for each span 20 feet. So I can complete these diagrams. Once you complete these diagrams, I can figure out the value of M ultimate for each part. From M ultimate, I can figure out rho and then area steel. I will continue next time. But the last step, we stopped here. We figured out the applied uniform load on the beam. Guys, do you have any question? Today, the topic is very important. Today, the topic is very important. We have many information. We started to understand something. What's going on? What's going on? We have some guides from ACI, help you to figure out the overall depth, the concrete cover, how can we design some guides to figure out the applied load and what is the value of bending moment, and where can I put steel reinforcement, at the top of the beam or at the bottom of the beam, based on the diagram. And remember, bending moment is drawn on the compression side. I'm talking about USA, because if you go outside USA, you will find something different. Okay, so bending moment can tell you where is the compression side. That means the tension side will be on the other side. So on the tension side, you have to put steel reinforcement, because steel reinforcement will support tension. Why? Because concrete is very weak in tension. Any question, guys?